So hello everyone. The first question is a hydraulic turbine is designed to produce 26.845 megawatt at 95 rpm under 15.24 of head. Laboratory facilities are available to provide 4.572 feet of head and to absorb 37.285 kilowatt from the model turbine. So we have to determine the approximate model test speed and scale ratio. And secondly, volume flow rate assuming a model efficiency of 86%. So here we have given a model and actual actual turbine. So the question given that the model power 37.285 kilowatt and head is given that 4.572 feet and efficiency is 86% and actual speed is 95 rpm and power 26.845 megawatt and head is 15.24 feet. So we have to calculate the model test speed. So for model test speed we know that for a turbine we know the relation n into under root p divided by h to the power 5 by 4. So here a model and actual value should be same. So by putting the value which is given in the question, we can see that the model test speed is coming out as approximately 566 rpm. And for the scale ratio, we know the dimensioning power coefficient. So by equating both the power coefficient and putting the value here, coming out the actual and model is 0.092 and this is the diameter of the turbine. By putting the value in this dimension power coefficients equations. And secondly, the second part of the question, we have to find out the volume flow rate. We know that efficiency equation we know. So efficiency equal to P by rho Z flow rate into head. So if we have to find out the flow rate of the model, so by putting the value of power rho Z and efficiency of the model is given and head, the flow rate of the model is coming out as 3.1746 meter cube per second. So the second question is given, conditions the inlet to the nozzle of a Pelton wheel are P equal to 448.2633 bar and V equal to 24.14 kilometer per hour. The Z diameter is given as 19.05 centimeter and the nozzle loss coefficient is K equal to 0.04. The wheel diameter is 2.44 meter. At this operating condition, the hydraulic efficiency NAH equal to 0.86. Calculate. We have to calculate A, the power output, the normal operating speed, the approximate runway speed, the torque at normal operating speed, and the approximate torque at zero speed. So for these, firstly we apply the Bernoulli's equation. That we know the Bernoulli's equation, the velocity of Z. So from Bernoulli's equation we can calculate the velocity of flow velocity of Z, and by putting the values, it's coming out as 96.45 meter per second. So firstly we have to calculate the power output. So for power output, we know the flow rate equal to pi by 4 into d square into v1, the flow velocity. So by putting the value of diameter and velocity, the flow rate is coming out as 2.73 meter cube per second. And again, the head loss, you know the equation, P1 by rho Z plus V1 square by 2Z. So by putting the value, it is coming out as 494.76 meter. So the power output, you know the formula for the so the power output you can find out in this equation, rho into Q into Z Hn. So we have the values. So rho we know 10Q and Q flow rate is coming out as 2.73 and gravity 9.81 and head is given and efficiency is given 0.86. So power output is coming as 11.39 megawatt. So we have to calculate the normal operating speed. For normal operating speed, on the velocity is as 0.46 the z velocity into z velocity, so it's coming out as 44.36 meter per second. So now for the operating speed, n equal to 60 into u divided by pi d. For the z, now by this we can, by putting the values, we can find it the operating speed, that is coming out as 347.39 rpm. And we have to find out the approximate runway speed. By this problem we can relate to the equation that we know the runway speed is equal to 60 into z velocity divided by pi into diameter. So by putting the values, we don't know the values. The z velocity is 96.45. The diameter is equal to also know 2.44. So by putting the values, we can easily get this runway speed, that is coming out as 755.32 rpm. Its part is we have to calculate the torque at normal operating speed. For a Pelton wheel, we know the formula to find out the torque. So for torque, we know the formula T equal to, that is torque, equal to rho into Q, flow rate, into V is a z velocity to wheel velocity, U, into 1 plus K. K is given the nozzle loss coefficient, is given in the question, cos P power and D by 2, that is diameter. We already know all this value, so by putting this value, I'm easily find out the torque at normal operating speed. They are coming out as 344,179.02 Newton meter. A K is equal to given as 1. K is 1. Yeah, normal operating speed. So K is 1. And last part of the question, so we have to find out torque at 0 speed, that is U equal to 0. So same equation, because we have to put that U equal to 0. So it is coming out as 3637368.55 Newton meter. So third question is, the reaction turbines at Niagara Falls are of the Francis types. The impeller outside diameter is 4.5 meter. Each turbine produces 54 megawatt at 107 rpm with 93.8% efficiency under 65 meter of net head. Calculate the specific head of this unit. Evaluate the volume flow rate to each turbine. Estimate the penstock size. So we have to find the penstock size. If it is 400 meter long and the net head is 83% of gross head, assume suitable data if necessary. So from this question, firstly we can find out which are given to us. So diameter is given 4.5 meter, power is given 54 megawatt, the length is given for 400 meter, and the speed is given 107 rpm, head loss is given 65 meter, and the distance is given as 0.938. So for specifics, we are already discussed about this in the first question. So specific speed we can find out as n into under root p divided by h to the power 5 by 4. So by simply putting this value we can find out the specific speed. So it is coming out as 134.72 rpm. And the volume flow rate, so flow rate we can find out q into p divided by x into rho gh. So by putting this value we can find out the flow rate, that is coming out as 90.28 meter per second. So after this we have to find out the penstock size, it is given as the question is given as estimate the penstock size if it is 400 meter long and the net head is 83% of growth has. Well, according to the question, so the net head equal to 0.83 of h not the gross head. So we can find out. So h gross head equal to net head plus hf friction head. So the friction head is coming out as 13.312 and friction head is also known as FLQ square, the flow rate square divided by 12 into d to the power 5, which is diameter. So by simplifying this value, diameter is equal to diameter means its size, the penstock size. So we can find out 3.89 meter. We can use Moody's chart. So using this Moody's chart and assuming penstock is made of concrete, so we got d by d naught, so is equal to 0.0015, and taking Reynolds number is 3 into 10 to the power 5, we got f equal to 0.004. By all this by putting all these values, the size is coming out as 3.89 meter. So last question, a propeller turbine has been designed to develop 22,000 kilowatt under a head of 20 meter whilst turning 150 revolution per minute. The relevant data is hydraulic efficiency 95%, overall efficiency 88%, outer diameter 4.5 meter, and diameter of the hub is 2.2 meter. Determine the runner fan angle at the hub and at the outer periphery, assuming that the turbine discharges without while at the exit. So simply for a propeller turbine, we know hydraulic efficiency. So for hydraulic efficiency, we know the formula, N is equal to VW1H1 divided by ZH to head. So efficiency, so velocity, we can find out as by putting all the values is coming out as 5.26 meter per second. And again, we know that in propeller turbine, the flow rate, inlet and outlet, the flow rate 1 is equal to volume rate 2. So 10 phi equal to Vf2 by Vf1 as it is propeller turbine. Now it is given in the question the overall efficiency is given. So N overall is equal to 0.88 equal to 222,000. So overall efficiency is coming out as 225,000 kilowatt. So now WP is equal to rho z QH divided by 1000. We can find the variable efficiency. So 25,000 is equal to rho z QH divided by 1000. So flow rate is coming out as 127.55 meter cube per second. So again, as it is propeller turbine, so the flow rate is equal to pi by 4 divided by d naught square by dh square into Vf2 square. This is diameter of the outlet and the volume flow rate. So volume flow rate 2 is coming out as 9.99 meter per second. So from equation 1, by putting this value, phi out is coming out as 15.74, which is runner angle and output. For runner angle at inlet, we have tan theta. Tan theta is equal to Vf2 divided by Vw1 minus V1, which is velocity, flow velocity. So after putting this value, we can see that the inlet runner angle is coming out as 18.2. So you can find out the values. So thank you.